and Tyler Beck. Today we're going to be talking about the Windows system components, terminal, services, and fast user switch. So system components are divided into user mode and kernel mode, and first we'll be talking about user mode. So the system processes kind of make up the operating system. They make sure that it functions properly. Basically, anytime the OS needs to perform a task, it uses these processes to get it done. So that includes I/O processing, memory management, anything that it needs to do, it will use these processes to do it. And two of the examples that you can see here are LSASS, which is the Local Security Authority subsystem, and CSRSS, which is the Client Server Runtime subsystem. So yeah, these pretty much just maintain the OS functionality and make sure that it's doing everything correctly. Services, on the other hand, perform background functions such as Windows Update, DHCP client, and remote desktop services, which we'll get into in a second. Windows Update just performs auto updates on the system, and DHCP client gets IP information automatically. These often run inside of svc host.exe, which you can see here in the diagram. And there's one main difference between the system processes and services. The main idea between it is the system processes are the core OS functions, which again make sure it's functioning properly. Services are kind of extra tools for extra functionality for the user to enjoy that don't necessarily that aren't necessarily crucial to the operating system working properly. So that's what they are. Then we have applications, which not much needs to be said about these. They're just general user applications like your browsers, your task manager, any apps that you may have installed. Those are all going to be this broader application. And so yeah, these are just general user applications. And then environment subsystems are another easy concept. They pretty much just allow applications that were made to run on other operating systems to run on Windows. It's kind of an interface that allows, let's say there's an application that was made to run on Linux. It will allow the same app to run on Windows using this environment subsystem interface. And there's one thing in this diagram that we don't talk about in this slide, which is the NTL DLL. This provides the interface between user mode and kernel mode, so it's how the two modes kind of interact and talk to each other. And yeah, that's what we have for user mode.
Now that we've covered user mode, we are now going to move into kernel mode. Beginning at the top layer, as you can see in the diagram, our system service dispatcher. That is essentially the gateway between user and kernel modes. So the process is as follows. Essentially, the user mode is going to make a API call, a Windows API call specifically here, which is then going to turn into a system call that the system service dispatcher receives, and then after that, the system service dispatcher uses something called the system service table to find the right kernel mode function or kernel mode service that needs to be used based on the API call and what's inside, the data inside. So we can think of the service dispatcher as essentially the gateway and the mediator between user mode and kernel mode that ensures that our system calls are sent to the right direction and used in an efficient manner properly, and the correct function is applied. Then we move into the kernel mode callable interfaces. As mentioned with the system service dispatcher, we were connecting the user mode and kernel mode. However, with the kernel mode callable interfaces, this is no longer the case. We could think of this as API calls inside the kernel. So there is no use of user mode in this case with the callable interfaces. We are strictly inside the kernel mode, operating everything, all our function calls All our processes are going to be in kernel mode here. So essentially one part of the kernel may need something from another part of the kernel. This is the basic concept of what these callable interfaces do. So for example, device drivers use this to allocate memory, create threads, processes, etc. This is good because we don't need to switch between user mode and kernel mode. This helps with our speed. This also helps with our security because there could be data breaches when we switch from user mode to kernel mode and back and forth. So the fact that we don't need to switch is definitely a benefit, which in turn improves our performance and makes it easier to ensure efficiency and execute these calls and etc. Now, broadening out a little bit, we're going to talk about the kernel itself. We can think of the kernel as the brain of the operating system, as many people like to say. The kernel makes decisions, manages resources, maintains stability. The kernel essentially makes sure everything runs smoothly and is, as we say, the brain, as I said before. Again, more things it does is process, thread, memory management. It does all that, interrupts and exception handling. It ensures all these things are running correctly and without hiccups, because a hiccup can be detrimental in the kernel mode, especially if there's attackers trying to breach and pose security threats. The kernel is making sure this is all running smoothly. Finally, we're going to talk about the hardware abstraction layer, which you can see is our bottom layer. This is the closest layer we have to the hardware before we get to the hardware itself, between software and hardware. The hardware abstraction layer essentially hides the hardware-specific details from the operating system, or abstracts as it is in the name. This enables Windows to run on different types of hardware without modification. So if you have hardware that maybe doesn't align, this hardware abstraction layer makes sure that you can use the Windows operating system with any type of hardware, whether that's AMD, NVIDIA, any type of hardware you may have. This hardware abstraction layer ensures that you can use it with whatever hardware you have, and that's essentially what you're going to get with the hardware abstraction layer right before you get to your hardware. So that is essentially the kernel mode. As a whole, we've covered pretty much everything you see in the picture from top down, and below this would be hardware, and up here would be the user mode, so everything in between is the kernel mode.
Here you get a really good visualization of that. You can really see how user mode and kernel mode talk to each other here. Using this NTL DLL interface, so essentially just system calls, and yeah, this is how it all comes together. So now we're going to talk about Windows terminal services. Before, when I was talking about services in user mode, I mentioned remote desktop services. These two things are the same exact thing with different names. It was renamed remote desktop services, but they both reference the same exact thing. The main idea is to host multiple simultaneous user sessions on a single server. So basically, you can be in one spot anywhere on any host, and you can begin a user session and connect to a terminal server over a network, and this allows you to do work on that server from any host computer that you want. So yeah, this is done via a remote desktop connection, or RDC, which connects to the remote desktop host. This is just the software behind it, and it is compatible with Windows, Mac, and Unix-based computers, so pretty much anything, any mainstream operating system is able to run RDC, which is very nice, especially if you want to use a different operating system as the terminal server. You can use a Windows client and run a Unix terminal server on your client. So it's really useful that it's compatible with all of these. So yeah, UI is presented by the client, the application runs on the server, so essentially all of the operations are done on the terminal server, and then again via the network, as you can see down here. It will bring back all the data and it will show it on the screen using the UI that's presented by the client. And this has a wide range of benefits, two big ones being remote jobs. So you can be anywhere in the world and kind of connect to this terminal server. So say there's your work computer in the office. Let's say you're remote, you're not in the office, you can connect to it on your own computer, and that can be very useful. And security is another aspect that's good for this, because we are not bringing the data into more places than necessary. So essentially, security is fulfilled since we are not replicating data unnecessarily. And one more benefit that isn't written on here can be that we are using a single server. So say several clients want to remotely connect to the same terminal server. This is easier in terms of overhead because you will only need to update one server. Any fixes can be done on one server, so that's another thing to keep in mind as well.
Now we're going to talk about fast user switching, or fast user switch as the formal term. Essentially, it's just allowing multiple users to share a single computer. So, for example, myself and Charlie can both be logged into one computer at the same time and switch back and forth between our sessions. This makes it easy to retrieve our user session because it's kept in memory. However, there's potential risks such as security breaches. It also uses more memory if you have two users or multiple users signed in at the same time. This makes the CPU work overtime, which could in turn be a negative effect if you're looking for optimal CPU usage. So those are just things to consider if you're going to implement fast user switching or use it on your personal level. Some things you may not be aware of is that fast user switching internally relies on terminal services that Charlie was just talking about previously. Each user session is technically a separate terminal session, even though it's local. So that's just something to take into consideration, and that may not be as known as it may seem. Also, GPU usage. The user session that is currently being used, or the foreground session, is the one that takes all the GPU usage and controls all the usage. So depending on what you have pulled up or logged into on your background session or the user session that's currently not being used, such as high intensity GPU usages, such as maybe a video editor, those might crash if your user session is not being used, just because the foreground session gets to control the GPU usage. So that's something to consider when implementing fast user switch. So that's GPU usage and that's fast user switch. So we covered system components, terminal services, and fast user switching, all in the Windows operating system. Thank you.